Hi, this is Don Allen, and we're going to look at Newton's Newton's method for iterations to find the zeros of an equation. The input that you need to put in, at least for this code, or I need to put in, is the function, the starting value, the tolerance. That is, if successive iterates are less than the tolerance, we say we have found a root and accept it and move on and look for more. The maximum number of iterations to make is if we exceed that, we just assume it's not going to converge. This is another condition you put into a program so it doesn't go into an infinite loop. Y max, that is a value such that if the derivative, the deflated derivative is less than the reciprocal of it, we stop the iteration, say we can go no further. And if the computed function value is greater than that value, we also stop the iteration, citing an error condition. M is the maximum number, capital M is the maximum number of roots we're going to look for, and the iteration will fully stop after finding M roots, even if there are more roots. So let's see what we got here. This is the function. It seems to have two roots, one at about 0 and the other about, looks like about 1.2. I asked Maple to solve the equation. Right there, it was unable to. As you can see down here, well, it's only found the root at 0, but it didn't find this other one. Let's see what the Newton method can do. Looks like Newton's method found two roots. And now what we're going to do, two roots, about 1.18, and the other is very close to 0. Let's plot them and see what we get. As you can see, the original function is in green, and the first deflated function is in red, where the 0 at 0 is still present. And the second deflated function has no zeros whatever. It's the blue function, strictly below the axis. Now what I want to show you is what happens when we change the tolerance. In this example, the tolerance was 10 to the minus fifth. What I'm going to do now is cut it down to just 0.1. That means we're just hardly at the root, and we say we found it. This is not a good practice, but let's just see what happens. So let's start the whole thing over. Run it. It still finds two roots, one at 0 and one at about 1.9. But now let's look at the plots. As you can see here, we have these spikes going on, and particularly the one at 1.2 for both of the deflated functions. The red one in this case is the second, the blue one is the first, the green one is the original function, so what you see is when you have this granularity of your approximation, you can achieve spikes in solutions. Okay, we're ready to try our second function now. Let's take a look at what it is all about. Let's go back up here and take a look at the graph. As you can see, one solution is about 0.6 and the other is about 2.2 in that vicinity. In fact, in this case, Maple has found them, not 0.6 but 0.35, and the other is about 2.15. What we don't know are the internal mechanisms Maple uses to find roots. Sometimes it finds them, sometimes it doesn't. But let's see what our program does here. Keep in mind, we're looking for about 0.36 and 2.15. And in fact, that's what we got, about 0.356 and 2.15. And let's take a look at the deflated versions. There you have it. The original function is in green, and the first deflated function there still has the 0 at about 2.15, the second deflated function has a zero at has no zeros except for the spikiness that's occurred. And even still, let's take a look at what the tolerance was. The tolerance in this case was 0.1. Let's change that tolerance now and see if we can get close enough to the actual roots that granularity disappears. Okay, we found about the same roots. They're within 1,000th or something, and you really can't see it too well unless you just study the numbers. But let's look at the graphs now. Now you can see the original function in green, the first deflated function in red, and the second in blue. No spikes on the graph at all because the granularity is too small to pick them up. Even still, you'll notice I'm plotting this using 100 points. If I bumped it up to maybe 10 or 15,000, you might see the spike. But here you have a screen that may be broadcast at 72 dpi, and then you're talking about thousandths of that, so it's not clear you'd even see it. Okay, are you ready for the third example? Okay, here's our third example. It's a polynomial. It's a fourth degree polynomial, as you can see. It's got four zeros of the function, four roots of the equation, and Maple has found them to be about 1.23, 2.1, and minus 0.78 and minus 1.55. Let's see what our program can do to find it. It found four roots, all about the numbers that we looked at above. Here they are right down below. And you see the thing did terminate because it couldn't find any more roots or exceed the number of iterations allowed. Let's do the big plot now and see what we got. Here we have, there's going to be five functions. The original function, which is in red, there's two red functions. The original function is this one. And then the next function we want to look at has three zeros. That would be the green one. Here, here, and there. That's the second one. The third deflated function has two zeros. That's the other red one. In fact, it's a parabola. It goes like here. It will be a parabola because you're taking a quadratic. You're dividing a quadratic into a quartic. And the fifth one is a straight line. That's the blue one here. And the last one is the fully deflated function, removing all of the roots. That means if you divide any polynomial by the product of x minus all of its roots, you'll get a straight line. And so we hit it. Just for grins, let's change the tolerance back down to 0.1 and see if we get any spikes in there. Here the tolerance is very small, but now we're going to make the tolerance just almost pretty big. And let's start the whole ball rolling again. Again, it finds something that looks like the roots, but there are differences in decimal places. But now you can see we have generated at least one spike at the leftmost root. Sometimes the other spikes don't occur, at least in Newton's method with reasonable functions, because the method is so fast and so accurate that it gets to the root before you know it, and the iterations are successively small. I mean, the differences are very small, despite the fact that your tolerance is quite large. Okay? So that's how the Newton's method works in practice and in color.